On today's lecture, we're gonna discuss about the need of getting models. Okay, because we have an aircraft. This is the aircraft under a study. Okay, this aircraft is expected to receive these input signals, as you can see in here, the set point for the pitch angle, the set point for the roll angle, and the set point for the yaw angle. And this aircraft will give us the measure of the speed in the x-axis, the measure of the speed on the y-axis, and the measure of the speed in the w-axis. Okay, you will see. So we need to describe in a mathematical form the behavior, the performance of this system. Okay, so the aim of today's lecture is to introduce the need to get these transfer function models for this aircraft. First of all, we will have a review of the aim of the course. Okay, the aim of the course is this. As you may remember, you have this video available in YouTube. Let's have a quick look. As you can see here, this is our ground floor lab in here. Okay, and you can see the aircraft is flying in an autonomous way. I will pause the video. Can you see here the computer? This is the remote computer that receives all the information of the navigation data and also the images that are being shot by the bottom camera of the aircraft. Okay, so the aircraft sends the computer by a Wi-Fi device, sends the bottom camera photographs in order to follow this red line on the floor, and then all the navigation data, the angles, the speeds, the accelerations, and the like. Okay, this computer will have inside all the control structures in order to decide what to do with the four rotors in order to follow this line on the floor. That's the idea. So this was our first autonomous flight. As you can see here, the aircraft is following straight line here. Now the line turns to the left in here, and you will see that the path following algorithm in the computer will tell the aircraft to turn left and then follow the line. That's a different objective because, as you can see here, we have a 90 degrees turn. It's quite more difficult to have a 90 degrees because here in the bottom camera there is a bit of confusion because we have a straight line and then this straight line turns into an horizontal line. So that's the problem. It can be a bit confusing for the aircraft. But as you can see here, it works fine. The performance is quite good. Well, as you can see, this movement to the left, right, and so on is because the aircraft is producing a very important wind here at the bottom. Okay, so the aircraft itself is disturbing it. Here we have short turns, as you can see, but this will not be our practical problem. Our lab problem will be the following. This is our lab work. You will see. Well, the main idea is that I have prepared like a software architecture in order to what? In order to have the aircraft being prepared to follow this line. Okay? So what it will be your work? Your work will be, first of all, the identification of the dynamic model that is behind this aircraft. Okay? So that's what are we starting to talk about on today's lecture, to find the dynamic model of this aircraft. Okay? Because we need the model in order to control the aircraft. Yes? Then, in a close future, we're gonna have an image processing algorithm. You will do it on your own, okay? Because we will have the bottom camera image, and this bottom camera needs to be processed in order to place the aircraft in opposition to the line. So we need at the end, we need to place the aircraft depending on where the line is going, where is the direction of the line. Okay, so that's the idea. So we will do all this work with me. So first of all, the identification of the model. Okay, we will start with this on Thursday. That's a heavy work, but I'm gonna tell you how. And then next week we will start with the image processing. Okay, I'm gonna show you how, and you will do it always by means of MATLAB computing software. Okay, well, let's go on. So that's the idea. I want you to follow this line. I have prepared all the architecture, and you will replace all the functions of the control of the aircraft, and then this is one of my students, the control of the aircraft, and then the image processing. Okay, well, here we have different applications. Here the aircraft must stop at every crossing in order to check that everything is going fine. And then the final application for this student was to follow a strange pattern here, to do like a snake. Every time it gets a crossing, it must turn 90 degrees, sometimes to the left, sometimes to the right. It's a bit different than here, because here the aircraft was always turning to the right. Okay, so here the application is more complex, because the aircraft, well, at the end, the computer needs to make the difference between left and right. It's not so easy, or as easy as it seems. And then a different application, but we are not going to work on that. It's to follow a color object on the floor. As you can see here, if we move the blue object on the floor, the aircraft tries to keep the distance more or less constant in order not to lose the object, as you can see. That's the idea. Okay, but we're not going to do that. We are going to follow the line. That's the idea. Okay, fine. So is it clear what we're going to do? Yeah.
Yep.
Fine. So we have this architecture. We have the aircraft itself, okay, that it's flying, and the aircraft itself has an angle control. I'm going to show you afterwards. So the manufacturer, that is Parrot, okay, the manufacturer has already built an internal control loop that assures us that the angle is has zero error. I'm gonna show you afterwards. So the aircraft is flying, and then it has itself an angle control. Okay. Here, at the bottom of the figure, we have a computer This computer will do the image processing, as I told you, and the speed control, depending on the relative position between the aircraft and the line to be followed. So for this objective, the aircraft sends pictures and navigation data to the computer, and the computer tells the aircraft what to do: take off, land, and the set points for this angle. Okay? The architecture means the following. We will do all the mathematical computations by means of MATLAB. Okay? Why MATLAB? Because we could use C, we could use Python, we could use any programming language. But MATLAB is so interesting for us because you are so keen on MATLAB. Okay? Yeah? You have worked with MATLAB previously. If we try to work on C or Python, the things will work better because these are optimum languages, but the problem is that we will do, or we will be expected to do, an enormous effort in order to make the things work. Okay? So I prefer for the application to be quite good performance, but in opposition, it will be so easy to work with MATLAB, because MATLAB has a lot of libraries in order to work with this kind of problems. MATLAB has a good connection with robot operating system. As you know, robot operating system is has been thoroughly explained by Professor Julian, so nothing to do on that. Then we have a computer with a Linux system. This Linux system takes control of a computer Wi-Fi communications card, and then we have a communication with the aircraft. So that's the physical and the software architecture of our application. Okay? Well, these MATLAB functions will include three different functions that are gathered in three different levels. Okay? First of all, we have the main. The main function, as you will see in a close future, will define all the communication devices, will define the gains of the controllers that you will tune, will define the set points, and then we'll send the command to take off, the weights of hovering, and define and start the timer. What is the timer? The timer is the most important thing because the timer will take control of all the functions to be executed at a constant time. Okay? So the timer will take control of all the software that is being implied in our problem in order to make all the communications to be done at a precise time. That is our sample time. Okay? The timer will receive the navigation data, will call the controller function, will receive the controller action, and will send this action to the aircraft. Because we have the computer that will calculate all the controller actions, but this action needs to be sent to the aircraft. So that's the role of the timer. Then the controller will receive the navigation data for the timer, will calculate the error, then will apply the control law with incremental algorithm. This will be the PID that is already known for all of you. Okay? And we'll send the controller actions to the timer, because the timer will send these actions to the aircraft. Okay? So that's like a general idea on what's our application which are the elements that compose our application. Okay. Well, so now if we focus on our problem, on my part of the course, we need to have a feedback control review. As you can see here, this figure is so familiar to you, should be so familiar to you, because we have a process that needs to be controlled. Okay, let's say, for example, that is the V on the forward direction. So the speed, the velocity, the linear speed of the aircraft on the forward direction. Okay, this is Vx. Yeah, this will be the controller output, that it's the input to this process. Let's say, for example, the set point for the angle. This angle will be the pitch angle. Okay, because the pitch angle will be affected, will be changed in order to make the aircraft to going forward. That's the idea. The disturbances could be, for example, the wind. Okay? Well, then here we have the controller, and the role of the PID controller is to compare our desire, our reference, our set point to the measurement of this real speed. So here we have the real value. In what? In millimeters per second. And here we have our reference. That's not real. That's the value we want to have in here. That's the idea. Then this reference is also in the same units, millimeters per second. So the role of the controller is to compare the reference with the real value and generate the error. That's the idea. And this error will be processed by means of the PID controller law in order to calculate the controller output and send this controller action to the aircraft. And as you may remember from the previous slides, we have here like some kind of a complex architecture in order to do all this process, to make all this process work. Okay. Here we have, this is my personal computer. This is the remote personal computer, and this is the drone itself. Okay. This data is sent by means of the raw system and so on. Okay. So I hope that you connect this block diagram with all the elements that are previously described in the architecture. Okay. Let's go on. What about this inner angle control loop? This inner controller will not be tuned or built or coded by us. Okay, this is coded by the manufacturer. So the manufacturer, the engineers, have defined the parameters of this inner controller. As you can see here, we have the process variable of the angle. Let's say that this angle could be pitch, roll, or yaw. Okay, that's only an example, but it could be pitch, roll, or yaw. So we have this multiplied by 3. We have this block diagram. We have this inner control loop for the pitch, for the roll, and for the yaw. That's the idea. Okay, so this controller is built by the own manufacturer. Okay, we suppose that the manufacturer has found the model. This is the model, the mathematical representation of the performance of the angle of the aircraft, and the manufacturer has tuned the parameters of this controller in order to make this feedback loop to have error equal to 0. That's the objective. So, what can we do with this aircraft? We can, for example, change the set point of the angle. Let's say that this is the original value, and this is our final. This is our reference. This is what we want the aircraft to do. So first, the aircraft has an original angle, and then we want to change this pitch angle, for example. So we apply a step function in here. We can do that. Well, at the end, we will do that in our lab work. Okay? We change this, and we forget about the problem of the control of this angle, because this is not of our interest. Okay? We will let this controller as it is. Okay? Important. This is the measurement of this angle. This measurement comes with the navigation data. Okay? This is a topic. You remember the topics? The topics in ROS, okay? The operating system for robots. Navigation data for this topic, navigation data has a lot of fields, and one field is the measure of every angle, the pitch, the roll, and the yaw. But we will not stop here, because here, this control loop has nothing to do on the speed of the aircraft, has nothing to do on the position of the speed, only with the angle. So we need to add a linear speed control loop. Here, as you can see, we have the inner control loop that we have dealt before on the previous slide. Okay? So if we suppose that this inner control loop is working perfectly, then we can tackle a different problem. This different problem will be to measure the linear speed of the aircraft. This linear speed could be Vx when it's going forward or backward, and when it's moving from side to side, it's Vy. Okay? Yeah, because if you remember, if the aircraft is looking forward there, okay, this will be the x-axis, looking forward. Okay? Fine. So if we can measure this speed by means of a transmitter, by means of a sensor, we can compare this. This comparison is code in MATLAB. Okay? I don't want to mislead you. Okay? All of this is a block diagram. Okay? This is a formal representation of our problem. But at the end, this comparison is code in MATLAB. This PID control law is code in MATLAB. So these are code lines in our software. Okay? Well, I have prepared all this software, all the structure. You are asked to give me the parameters KP, KI, and KD for every controller. Is it clear, the aim? So your lab work will be to give me these parameters for Vx and for Vy. Okay, that's the aim. And we have a session in order to show you how to do that. But it's your work, okay? I only will replace the default parameters of the controller in MATLAB by yours, by your parameters, okay? And we will check the aircraft inside. So we will go to the lab in order to check the performance of the system. Is it clear? Well, this is only one work you're gonna do, okay? We have more work to do. You remember the image processing and so on. But the main idea is that if you want to get these parameters, these tuning parameters, you must know the dynamic behavior of the system. So the first question will be, what's the mathematical model that describes how my angle turns into a linear speed? That's my question. Okay? So the question to be answered at first is to find the model that will give us the relationship between the angle and the speed, the linear speed of the aircraft. Okay? Because if you don't know how it performs, you cannot tune the controller parameters. So that's the idea. Okay, but that's the linear speed control, but nothing to do with the position of the aircraft. Okay? So we need to add another loop. As you can see here, we have the inner loop, or if you prefer, the angle loop. Okay? But then here, as you can see, we have the linear speed. Okay, but we want the aircraft to follow a line. Okay? In order to follow this line, we need to control the position of the aircraft. So we have another mathematical relationship between the speed, the linear speed, and the position. But what's the problem? The problem is that it's not so simple, because it's not so simple. We have not a position sensor. Okay? Why? Because we are flying indoor. Okay? That's the problem. We are flying indoor. So nothing to do about GPS signal or similar. Okay? So we will use artificial vision. We will use the zenithal camera, so the bottom camera of the aircraft. Okay, that's the idea. So this bottom camera will send the image to the computer, and this computer will do the image processing, and then will give the position of the aircraft in comparison with the position of the line. Okay, the line to follow. Yeah, so the aircraft maybe is far. There is a distance d from the center of the aircraft to the center of the line. Okay, so the controller action, because we will compare the center of the line with the actual position of the aircraft, this will give a position error, and this controller will be we will expect that this controller will give the set point of the speed of the aircraft in order to move the aircraft and locate the aircraft just on the line. Okay, tracking the line. That's the idea. But this is a PID. This is a PID. But this controller is not a PID. Okay? This controller is this controller in here, and then this operation in here. Now it seems quite complex. I'm only introducing my part of the subject. Okay, we will see this thoroughly, yeah, in the close future. But as you can see here, V is the distance between the center of the aircraft and the line. Okay, so the control action will depend on D, obviously. The greater the D, the greater the control action. Okay, and then the angle. So maybe the direction of the aircraft is this, while the line is this. So there is an angle. Okay, the direction is different. So we need to turn in order to follow strictly the line. Okay, and then L is a parameter that is chosen by the user. Okay, I'm going to explain you how. Okay, there is a specific session on path tracking problems. Yeah, this is what we call a path tracking problem. When you want to follow something or someone, okay? Path tracking. Okay, so this variable in here, this gamma in here, will define the angular speed at the end. As you can see here, we have this gamma. Will define the angular speed of the aircraft, because if the angle and the distance are different from 0, the aircraft will turn in order to follow the line. That's the idea, okay? But I repeat, I'm only introducing this. Now it's only for showing that at the end, it's not a huge problem. It's not so complex. It will be so easy to explain. Well, at the end, this bottom camera will give us this kind of photographs, okay? This is 1/9 of HD, so this the resolution is N HD. You will see, okay, so it's 1/9 of the high resolution, of the high definition image or picture. We will do some kind of an image processing procedure, okay? Because the problem is that despite you can see clearly a red line in here, it's quite complex for a computer to detect that here there is a red line. Why? Because as you can see, this red line is placed just on the floor. Okay, at the end it's a red tape on the floor, and here I have from black to white. Okay, the problem is that if I take a picture with the RGB matrices, okay, RGB, we have the light intensity for R, the light intensity for green, and the light intensity for blue, okay? The problem is that here I have a lot of colors, because I have a lot of gray intensity colors in here, and I have different combinations of RGB. So if you have a look at the R matrix, it will be so hard to find a red line, despite you think it's so easy, okay? I'm going to show you in a session what to do with this image in order to tell the computer that there is a clear line in here, okay? Then we will linearize this image. There is no tricks in here. You can go from this image through this clear image, and here you can see clearly the perfect red tape on the floor, okay? But that's not the end of the image processing, because we need to get the distance and the angle. You remember from the preceding slide, the distance and the angle, because the algorithm of the path tracking needs these two measures, this in millimeters or meters, depending on the units we will use, and this angle in degrees or radians, okay? Because we have the reference axis of the image, but the reference axis of the drone is quite different. We will be expected to do some kind of a translation and rotation of this axis. I'm going to show you. As you can see here, we will learn a lot of different things in order to make this aircraft to fly autonomously. Well, in order to get this objective, we have this planning. We today gonna talk about models. We will talk about the identification procedure in order to get these transfer functions on Thursday. Next week, okay, we have a day off in here because it's holiday, but you will have like a video peel, okay? So you can have a look at this video peel on 13 or 14 of October, okay? In order to be prepared for the Cascade session The cascade control is this control that is you have different structures when they are nested to each other. Well, you remember the angle control, that is the inner loop. Then we have the speed control outside. Then we have the position control outside. So we have three loops, three control loops, three feedback control loops, and they are nested one to each other. So that kind of nesting control loops is what we call a cascade control structure. So Julian will be back in here on the 15th of October. And then finally, I will explain you the image processing on the 19th of October. And finally, the path tracking and the state machine and the exam will be all in class. Here we will meet at the ground floor lab. Okay, here we will meet at the ground floor lab. Okay, this is the exam. Okay, the exam will be with your own computer. Okay, if you're in trouble with the installation of MATLAB or anything, don't hesitate. Ask us. Okay, send us an email and we will help you as soon as we can. Okay, because you will need your own computer for the exam, so everything must work perfectly. Okay, and we have planned a visit, a day off, in order to visit a company that is the objective of this company is the autonomous flight of drones. Okay, so we have planned this. Obviously, we depend on the pandemic situation. Okay, but we feel so optimistic. So we hope that we can do this visit. Okay, because it's so interesting for you. Okay, any questions or doubts about the planning?
Yeah, there is a question.
Well, one by one. Sorry. Yes.
Well, there is a question in the chat. If will it be practical or write an exam?
Okay. Our intention is always to have a practical exam. Okay. Yeah. But it will be so easy. It's an optional track. Okay. Our interest is for you to learn a lot of things, as you can see, image processing and identification, these kind of things, and to show you that all these strategies, all these mathematical procedures will help us in order to fly autonomously a drone. Okay, and you will see it for real. So that's not a simulation model. That's for real. So our interest is that this exam is practical, it's practice. Okay, so you need your own computer. And I'm going to tell you right now what I'm going to ask you for this exam. For example, I'm going to give you an image and I want you to get the red line for this image, for example. Okay, easy, because you will you have done this in the lab. Okay, in a close future. Okay, you will do this in the lab. Okay, another thing, I'm going to give you some data of a real aircraft, and I'm going to ask you to find a model for this, for example, for the pitch angle and the speed as the output. Okay, so you will do this in your lab sessions. Okay, so the idea is to do it on your own with absolutely no help. That's the idea. Okay, you with me? It's not a tricky exam. So please don't think that it will be a more difficult exam because it will be a practice one. That's not true. Okay, it will be so easy because you can check the results. It's better to be a practical exam because you can check the results. Okay, I have only given you some examples, but then I can ask you something about PID control or something like that, okay? And we're gonna give you an example of this, this exam, yeah? It will not be a surprise. You will be perfectly informed. Clear? Is it clear?
Yeah, is it clear? Thank you.
Fine. Okay. So another question?
Yeah, I had one more question. So is the visit or the outing mandatory if finally we do it?
Well, it could be. Why? Because do you have some issues for this day? Are you working or something? Because it's so interesting for you. So, well, at the end it's a lab session, and it should be mandatory, okay? But if you have some kind of, I don't know, I'm out because I don't know, I'm working far from home, I don't know, okay? Working abroad, I don't know. If you have some difficulties, we can discuss it, okay? But at first, we are really excited about this. So at first, is mandatory, okay? But we can talk about this. I don't know. We have 4 weeks in order to discuss. If you're in trouble, I don't know. But personally, okay? Not now in public, okay? Fine. More questions? Can I go on? Yes?
Yes.
Everything right? Fine. Well, I have a single screen computer, so I cannot have a look at the chat, okay? So if you have some interesting question, you can stop me at any moment, okay? Because I cannot have a look at the chat while I'm doing the presentation, okay? Well, so remember, we have, first of all, our objective is to design the speed control of the aircraft, the linear speed control of the aircraft, because we have the process variable of the speed, we'll have a set point for this speed, okay? But this set point for this speed will be compared with the measurement. Remember that this measurement will come from the navigation data, okay, of the topic, okay, the navigation data. I will get the Vx, for example, the Vy, okay? So by a single line in my code, I will compare both magnitudes, okay? This is my reference, this is the real value, the estimated speed of the aircraft, and I'm expected to build, to tune, okay, and tuning this controller, okay? Tuning means finding the proper parameters, okay, the own parameters of the controller. Yeah, this is also a code, a single line in my code, okay? Well, this is the inner control loop, so nothing to do about this. You cannot touch anything in here, okay? Well, you can, but we will not do it, okay? Because if we touch something in here, this subject will last 3 months, okay? And that's not our objective, okay? We will suppose that this works perfectly. So the problem now is that I need to describe the behavior of all these elements by a mathematical model, okay? Are you with me? Do you catch the need for this mathematical model? I need to design a controller for the speed. I can measure the linear speed. I can specify my reference, the speed, I don't know. 10 millimeters per second. I don't know any speed, okay, any linear speed for the aircraft. This will give an error of the speed because I'm comparing both magnitudes, okay? And this controller will calculate the controller action, but this controller action is applied on a system, and I don't know the mathematical model for the system. So if you don't know the mathematical model, you cannot design a speed controller. You with me? That's very important. You cannot apply a control strategy on something that you don't know. Okay? So first of all, what's the model behind this? Well, we have a lot of models. We have nonlinear models, yeah. We have linear models, and for these linear models, we have state space models and transfer function models, okay? Obviously, the best models to use are state space because they bring us an inner description of the energy of the system, okay? You can know all the inner variables, the currents, the voltages, the accelerations, the speeds of the system, and so on. While this transfer function in opposition to the state space models, this transfer function will only give us the information of how is the output related with the input, okay? What's the relationship between the input and the output? Nothing to do with the inner variables, okay? So if we use transfer functions, we miss some important information. But what's the problem? First of all, why we don't use nonlinear models? Because these nonlinear models will bring controllers, or the tuning strategy will be so complex, okay? So these models will not be used. Why? I know the nonlinear model is so precise, is a good approximation on the behavior, on the performance of the system, is a good model, but these kind of models will make so difficult the design of the speed controller. Okay, so that's the reason why we don't use these nonlinear models. Yeah. On the other hand, we have the linear models. That is okay, fine, but we have two different branches in here: state space or transfer functions. State space seems to be the good choice. Okay, why? Because this kind of models, you remember, this kind of models. Have you ever seen that? Okay, well, we will discuss this in next class. Okay, these are models with good information of the energy, of the internal energy of the system. But the problem is that we don't have the equations of our system. If we don't have the equations of our system, we cannot use the physical laws. Okay? We cannot use the physical laws. Why? Because we don't know perfectly, in a precise form, the power of the rotors. We don't know the moments of inertia of the aircraft. We have a few information on the system. So our strategy will be the following. We will send an input signal to the system, and we will record the output of this system. And by means of this output and the input of the system, we will be expected to find the model. And the easiest model to find, that can be found by only this information, the input and the output of a system will be a transfer function. So that's why we're going to use the transfer functions from now on. Not the state space, but the transfer function linear models. Okay? What about the dynamics of the system? If I affect the pitch angle, there will be a change in Vx. It's clear, because both variables are related one to the other. Okay? But the question is, will it be any change on the y speed? Will it be any change on the angular speed of the aircraft, of the yaw? This is the yaw. This is the yaw. This is the direction of the roll, and this is for the pitch. Okay, as you can see here. Okay? So the question is, are there crossed relationships between variable? I can assure you about my experience in the past that this aircraft has no crossed relationships. That means that if you touch the pitch angle, there is a slight affection in here, but it's not significant. It's like a disturbance, a small disturbance. And the same goes for the roll. If you change the roll set point, this is an angle, okay? You change the speed on the y-axis, okay? The linear speed on the y-axis. And obviously, you affect slightly the linear speed on the x-axis, but this affection is quite small in comparison with the direct affection. So we can assume that the relationships are only direct. Okay? So this makes the problem so simple. This turns our problem to be so simple. Okay? So now we need to measure this, compare with my Vx set point, then to design a PID controller in here, and to apply the controller action to the pitch angle. And you do this thing multiplied by 3 for the roll and for the yaw. Like this. This is a Simulink block diagram, as you can see here. We'll have the set point, can you see here? Step for the pitch, for the roll, and for the yaw. The comparison, the controller is a PI, so it's more simple than a PID. There is no derivative action, so a PI is enough. Here we have a saturation. Okay, in order not to make this controller action so huge or so small. Okay, that's the idea, to keep the control action between limits. Yeah, and this are the transfer functions you are expected to find. I will give you output data, input data of a real aircraft, and you will be expected to find these transfer functions. We will tackle this problem next Thursday. Okay? The same goes for the roll and for the yaw angles. Okay? What are we going to use for this objective? The system identification toolbox in MATLAB. Okay? You can use, you can type at the command window system identification, or in all the platforms ident. Okay, ident. That's the same. System identification or ident. Then, as I'm going to show you next Thursday, a graphical user interface is opened, and then I'm going to show you on Thursday how to use that in order to get these transfer functions that are our objectives. Okay? Well, as you will see on Thursday, this system identification toolbox will help you in as a graphical tool. By using a graphical tool, then you can watch the input, the output. You can manage all the signals and then get the model, and finally to validate this model and check that the model approximates the real response of the system. That's the idea. So thanks to the system identification, we will find the transfer function of our aircraft. Once we have the transfer function of the aircraft, we are expected to design the controller. Okay? We will use very simple and widely known and most celebrated methods. One of these is the modified direct synthesis. I'm going to explain how it works on the proper lecture. Okay, it's not the next lecture. It will be in a week. Okay, but at the end, the controller. Well, you have, remember this structure, the comparison. Here I have my PID controller. This is my controller. Then here is the transfer function I have found from empirical data. This is the set point, and this is the controller. Sorry. Okay, so this controller, the expression for this controller can be obtained thanks to this formula. Okay, this formula, I will explain it to you thoroughly. This formula comes from the direct synthesis method. Okay, so nothing to do with this right now. Okay, I'm going to explain it to you in a close future. So now, as you can see, for this controller, we need GD and G of S. G of S is the identified model, okay? While GD is the desired, D comes from desired. This is the desired behavior of the closed loop system. So GD tries to answer the question, what's the performance that I expect from the closed loop system? This is GD. For example, a first order system with a static gain of 1 and a constant time of 10 milliseconds. For example, this is the constant time and this is the static gain. Why the static gain equals to K? Because this value in here, A, I hope that after this changes, this is A. So A minus A, the error will be equal to 0. That's the idea, okay? And then this is the speed, the expected. This is a measure on how fast this controller reacts to the changes in the set point or to any disturbance that happens in here, okay? So that's the idea. And what's the problem that will be associated with this? As you can see here, this transfer function is chosen by you. You decide what's the desired feedback performance, okay? But this transfer function in here depends on the aircraft. And I can assure you that it's not so easy. This G of S is a long polynomial transfer function. Okay, it's quite long. It will be a high order polynomial. Okay, so one of the strategies that we will do in a close future will be to reduce the model order. I'm going to show you how, and I'm going to show you now an example. Let me throw you a question. Does it ring a bell to you, the Ruth stability criterion?
Yep.
Have you heard about that? Am I right? Yeah? It's about stability. You remember? From cause number 1 of control. Okay? So, now we're going to use this Ruth table in order to reduce the model order. I'm going to show you. Well, first of all, let's have a review. Well, everything is gathered in here by contribution by Krishnamurthy and other authors. Okay, the contribution is quite old. Okay, it's more than 40. Well, it's 42 years old. Yeah, and this contribution talks about the model reduction using the Ruth stability criterion. Why it is so important? I remind you that on many controller formulas, the transfer function appears in these formulas, okay? So if the transfer function results in a very huge order transfer function, then the controller will result in a high order controller, okay? So there is a strategy in order to reduce the order of the controller. And we do that because at the end, everything is done by means of a computer, okay? This computer has a TS, sample time, okay? This sample time is as short as possible because you want to have as much information as possible from the system, okay? So all the operations, all the control operations, all the image processing operations, and the rest must be done within this sample time period, okay? So that's why a controller C of S that it's so long, it will be so difficult to manipulate, to operate with these polynomials in a short time sample. That's the idea. In order to be practical, this is a practical issue, okay? On the blackboard, everything works. If you apply this formula in here on a blackboard, everything works, okay? You can get C of S if you have G and GD, okay? It's easy. But the problem starts when you have to code this on a real problem. The aircraft is expected to fly, so you cannot bring a controller so long to this computer, okay? That's the idea. So that's the need of our model reduction. So, well, let's go back to the Ruth table. I'm not doing a first course of control, okay? Only to remind you that if you have a polynomial P of S, you have here P of n minus 1, and so on till P0. This is a sorted polynomial, okay? The first two rows of the Ruth table are built by means of these coefficients of the original polynomial. And you know that G of S is a numerator over a denominator, is a fraction, okay? A ratio of two polynomials, okay? So this P of S will be n and d. So the problem, the model reduction will be done in terms. First n, then d, okay? We'll build two R matrices, Rn, Rd for the numerator and the denominator, okay? I'm going to show you an example afterwards. Well, at the end, these coefficients are calculated by the Euclidean division algorithm, okay? It's the Sturm recurrence, yes, Sturm recurrence, okay? Now I'm not gonna be so long on these calculations. It will be written in the pill, okay? Yeah, but you will be given a MATLAB function that does the thing. I'm going to give you a function called root table. This function is not in your MATLAB by default. I have coded this algorithm, okay? And let's have a look at this example. As you can see here, we have a controller that is a third order controller, yeah? That's the idea, as you can see. It's a third order because here we have a third order polynomial, yeah? Then I'm going to build the root table for P1, well, P1 this, or the numerator, and this the denominator, whatever you want, okay? Well, the root table is this, yeah? That's the table, but this is on the common window environment, as you can see. And then the root table for the denominator. As you can see here, the coefficients 1, 2, 1, 1, 1, sorry, 1, 2, 1, and 1. Okay? And then all the calculations. Right? Well, the important thing in here is the following. On a root matrix, let's go back here. On a root matrix, if you move to the right, you decrease 2 degrees. Can you see here? Pn, you go to Pn minus 2. Pn minus 2. You with me? You are decreasing 2 degrees when you move to the right. Okay? But when you go down, you decrease only 1 degree. You with me? So the root matrix, if you move to the right, you decrease 2 degrees. If you move down, you decrease 1 degree. This is a property of Sturm recurrence. Well, okay, nothing to do right now. So the important thing is that we will decrease the order of these polynomials thanks to this property. You will see. Let's have a look at this polynomial in here, at the root table of this polynomial. As you can see, the original is s power to 2 plus s plus 1, okay, squared s plus 1. Okay, so this is squared s. If you go down, this is minus 1 degree, okay, you with me, s, and this is s power to 0, you with me? Yeah? And this is s power to 0 because if you move to the right, you decrease 2 degrees. I hope that it's so clear, okay? Fine, so if you want to decrease this polynomial 1 degree, you must take not the first row, but the second row of the root table. And as you can see here, if you start, let's go to the original polynomial. The original is 1, 1, 1. 1 here, and 1. Let's go to the denominator. 1, 2, 1, 1. 1, 2, 1, 1. You with me? So you first go down, then to the right, then down, to the right, and down, and so on. Because I remind you that on the root matrix, when you move to the right, you decrease 2 degrees. When you go down, you decrease 1 degree. Okay? So now, let's go back to the numerator. If you want to decrease 1 degree, you must not take the first row. You must take the second. So it will be 1 and 1. You cannot continue because you have reached s power to 0. So this transfer function for the numerator can be approximated by 1s, can you see here, plus 1 s power to 0, that is nothing, okay? Let's go to the denominator. As you can see here, this is the original. If you want to decrease 1 degree, it will be 2 So 2s, now it's not 3, because I have decreased 1 degree. S power to 2 plus, go down, 0.5, 0.5 s plus, now I go to the right, 1, 1, okay? So now I have decreased 1 degree for the numerator and 1 degree for the denominator. And this simple method has a very interesting property. You will see. Here, I have built from the original the transfer function we have discussed previously. Can you see here? Yeah, I have decreased 1 degree in the numerator, 1 degree in the denominator. Here, 2 degrees in the numerator, 1 degree in the denominator. Here, 1 degree in the numerator, 2 degrees in the denominator, and finally, I have reduced 2 degrees in both polynomials. Okay? Obviously, as soon as I get so far from the original transfer function, the approximations will worsen. Okay? So it will be worse. Okay? Well, let's have a look. Here is the step response. Well, the original one is blue. Can you see here the blue line in here? Yeah, it's an underdamped system. As you can see here, we have a peak in the transient response. Okay, then can you see the approximation G1? So if you decrease 1 degree in both polynomials, is the red one. Okay, as you can see, the peak is bigger, so it's not a good approximation. Okay, so it seems that I'm lying to you. But the important thing will be here. Okay, now I'm only joking. Yeah, here in the other transfer function G21, I have decreased only a single degree, or 1 degree in the denominator. Okay, the denominator is the same, as you can see, but the numerator has been reduced in 2 degrees. Okay, as you can see, it's the yellow one, and well, more or less it's quite similar to the blue and the red one. So, okay, this is a quite good approximation on the time response. But I'm not satisfied. As you can see, this purple line and the green one, these 2 transfer functions, they have nothing to do because one is doing this and the other one is doing this. So absolutely, they are not interesting. Well, let's have a look at the frequency response. Here, the panorama is so interesting. Well, the original system, remember in blue is the original one, has a resonance peak. Can you see here the resonance peak? Okay. And can you see that the yellow and the red ones are so close to this resonance peak? This polynomial is a good approximation of the dynamics all along this bandwidth. You remember the bandwidth? Okay? It's a good approximation. So, if this is a controller with this original bandwidth, can you see that the red and the yellow one are quite good approximations on the frequency domain all along the bandwidth, while obviously the purple and the green are not good approximations. I know. Okay? But the important thing is that if you don't decrease, you will have an exercise on that, okay, with a huge polynomial. And you will be asked, how long can I reduce my transfer function in order to have an acceptable approximation of the original transfer function?